In this lesson, we're going to have a look at some examples that involve a two-step experiment, right? Now, before we get into it, what we're going to try and do in this particular lesson is we're going to try and focus two-step experiments with the help of a tree diagram. Now, before we jump into the first example, right? Couple of hints, right? A couple of useful hints that can help us through this particular section, right? Whenever we're talking about two particular words in probability which are really significant, right? And or, right? These are two words that are really significant probability, right? Anytime we can start using these words, it gives us direction in terms of what operations to take into account for calculating the probability of different events or experiments, right? The basic cue I can give you is anytime there is a use of the word and, the operation that is involved is multiplication, right? And anytime we use the word or, the operation that usually involves is an addition, right? And that gives you a starter for this particular topic, right? So with just that basic information, let's just jump straight into the very first example. Right, so we have a bag, right? The bag contains 3 red counters, 1 blue counter, right? A counter is chosen at random. A second counter is drawn with replacement, right? The most important factor of this particular question here is the second one is drawn with replacement, which means what they're saying here is they're drawing a first counter, right? Having a look at the color, putting it back into the bag, and then withdrawing a second counter, right? That's a really critical aspect that's going to help us design our tree diagram in this particular case, right? So just with that, obviously the first part of the question saying show the outcome and probabilities on a tree diagram, right? So two-step experiment. The 2 steps are withdrawing a first counter is the first step, and withdrawing a second counter is the second step, right? So that's what we're going to do first. So we got 4 counters in total, 3 red, 1 blue. Right, so the first counter, when we go ahead and withdraw the first counter, we got 2 options. We can either withdraw a blue counter or a red counter. Right, what are the chances of us withdrawing a red counter? That is going to be 3 out of 4. So when we draw a tree diagram, right, in the branches of the tree, that's where we mention the probabilities of those individual tasks. Right, now when we withdraw the first counter, the chances that it's a blue one is 1 out of 4. Right, now another critical factor for us to realize is when we branch out, the total of all the branches is always equal to the total probability, which in this case is equal to 1, right? So it should always add up to 1, right? Now, when we draw the second counter, right, remember we're putting the counter back into the bag, which means we still have 4, 3 of which are red, 1 blue, right? If the first one was red, we have 2 options, right? A red and a blue counter, right, with the same set of probabilities, right? If the first one was a blue, then we can have a red or a blue counter as a second option, right? And again with the same set of probabilities, just solely because of the fact that this is an experiment which involves replacement of the first counter. Right, so what are our options? So the different outcomes we could possibly get in this particular experiment is a red and a red counter, a red followed by a blue counter, a blue followed by a red counter, and a blue followed by a blue counter. Now you might also want to work out the probabilities of these individual events, right? So the way we can work out a red and a red counter, remember when I talked about earlier, anytime we use the word and, the operation that is involved is multiplication. So the probability of a red and a red counter is going to be 3/4 times 3/4, which is just simply 9 out of 16. Similarly, a red and a blue counter is going to be 3 out of 16. A blue and a red counter, 3 out of 16, and a blue counter is going to be 1 out of 16. And again, you know, if you notice this, all the different possibilities across this particular experiment, we got 4 outcomes, and all of them, if you add them up, it's just going to give you 16 out of 16, which is going to be equal to 1, right? That's always a good way to check if your answer is correct or wrong, right? Now let's jump into the second part of this question, right? The second part of the question is saying what is the probability of choosing a red counter then a blue counter, right, which is the second outcome that we have in here. So the red followed by a blue counter, right? What are the chances of that happening? The chances of that happening is equal to 3 out of 16. Right, beautiful. The chances of us getting 2 blue counters, that is our last outcome there, right? So 2 blue outcomes, so B and P equals 1 out of 16. At least 1 blue counter, right? So at least 1 blue counter means we can get 1 or a 2, right? So the options that is going to suit us for this third question here, right, which is at least 1 blue counter, is 1, 2, and 3, right? There are 2 ways we can go about this question, right? We can basically say, so at least, I'm just going to write this down, 1 blue counter, right? We can go ahead and add these 3 options together, right, which is going to give us 3 plus 3 plus 1, so 7 out of 16. Or we can simply go use the complement, at least 1 blue counter. What's the opposite to that? That's no blue counters, right? So that's going to be same as 1 minus 9 out of 16, which is also going to give you the same answer, which is 7 out of 16. Right? So in this particular case, there was only 3 options for us, right? So we could basically go 3 on 16 plus 3 on 16 plus 1 on 16, it's giving us a 7 on 16. Or we could use the complement, which is 1 minus 9 on 16, which is the probability of no blue counters. Okay, right, so that gives us that particular question. Now let's last part of the option, 1 blue and 1 red counter, right? 1 blue and 1 red counter, right? I'm going to use the different color here, right? Now, unlike the first part of this question where they're saying a red followed by blue, in this question they're not talking about the order, right? Which means they don't care which order we're dealing with. So which means we have 2 options. We can get a red and a blue counter, or a blue and a red counter, right? Remember when we use the word or, what is the operation we've got to take into account? We've got to take into account the addition operation, right? So the fourth part of this question, right, probability of blue and red counter, there are 2 options for us. Either we could get a red followed by blue, or a blue followed by a red, right? So if we add the 2 probabilities together, so 3 out of 16 plus 3 out of 16 gives us 6 out of 16, right? In this case, we can simplify this further, right? Dividing both of them by 2 gives us a probability of 3 out of 8, right? And that completes that first question that we're dealing with. Now, I've just added this to this question, right? What if I was to redo this question without replacement, right? What I mean by that is, right, we take out the first counter, we don't put it back in, right? And then we take out a second counter. Let's see how the tree diagram is going to look like if we were to do this question without replacement, right? So for the first counter, we still have 4 counters, right? 3 red and a blue, right? So which means the first part of it's going to stay the same. A red followed by the blue, with the probability being 3/4 and 1/4. Now, when I go ahead and withdraw my second counter, this is where things are going to change, because remember we talked about no replacement, which means whatever we take out in the first attempt, we don't put it back in the bag, right? So which means we've already taken out 1 counter out of the 4, so which means we're left with 3 counters, right, for the second part of this experiment, right? So if the first one was a red, right, how many reds do I still have left? I still have 2 reds out of the 3 that are left, right? So 2 out of 3, and then the blue one's going to be 1 out of 3 for the second part of the experiment. Now, if the first counter was a blue one, right? If the first counter was a blue one, for my second counter, I still have all 3 reds left out of 3. So 3 out of 3, which is just simply equal to 1. Right, I have no blue counters left, which means the chances of me getting a blue counter for the second attempt is going to be equal to 0. And again, I need to focus, I want you to focus on each of the combination of branches, right? Each combination should always add up to 1, right? And that's the key to drawing a tree diagram, right? Now, if I was to represent my outcomes in this case, so we're going to have red and red, red and blue, blue and red, blue and blue, right? And the probability of their outcome is going to be, for the first one's 3/4 times 2/3, so times 2/3, right? That's going to be 6 on 12, right? Which is simply 1 on 2. Right, similarly for the second one, 3/4 times 1/3, 1/4, 1/4, and 0. And again, if you add all the 4 probabilities, that is going to be equal to 1, right? That's again a second check for you to do this question, right? Now, for the rest of the section, right, these things are going to be the same, except we're going to be using these probabilities instead of the ones that we had in the previous tree diagram. That's going to be the only difference for the rest of the question. All right, moving on. Let's look at a second example here. All right, this time we're dealing with a pack of cards, right? Understanding of pack of cards is really, really important, right? So the kings and queens from a deck of cards are shuffled, and then 2 cards are chosen. Right, now the key part here is they are only shuffling the kings and queens from the deck of cards, right? In a deck of cards there are 4 kings and 4 queens, right? So which means we have 8 cards in total that we're shuffling at the start, right? This time they're not using the whole 52, they only focused on the 8 cards, 4 kings and 4 queens, right? And that's really important when it comes to probability, is reading the question, right? Then they're choosing 2 cards, one after the other, right? Find the probability that the 2 kings are chosen, right? There's 2 parts of the question. If the first card's replaced, if the first card's not replaced, right? So if I was to quickly draw up a tree diagram for this particular scenario, right? Let's talk about with replacement, which means we take out the first card, put it back in the deck, and then shuffle it again. We pick out a second card. So with replacement, which means we're going to have 8 cards for both experiments, right? So the first part of the experiment, we could pick up a king or a queen, right? So 4 out of 8, same as a half, so they both have chances of 1 on 2, right? For the first card, right? And the second card, we're still gonna have 8 cards still left, because remember we are replacing the cards, so the probabilities are going to remain the same. Right, now in this question they're only focused on the probability that 2 kings are chosen, right? So the chances of 2 kings being chosen is going to be equal to a half times half, right? That is just simply equal to a quarter. Right, and that completes this particular question, and that's the answer to this first part of this question. Right, now what if the first card was not replaced? So if I was to redraw the same diagram, right, I'm going to do this here so we can all see it in the same box there, without replacement, right, which means we take out the first card, we don't replace it, which means for the second card we only have 7 options left, right? So first card, we got 8 options, 4 kings, 4 queens, right? So which means the probability is going to be 1 on 2, so 4 out of 8, which is same as 1 on 2. Now for the second card is where things are going to change, because remember we are not replacing the first card. So if the first card was a king, right, how many kings am I going to be left with? For the second card I'm going to be left with 3 kings out of 7 cards, so which means the probability of a king is going to be 3 out of 7. Right? If the first card was a king, I'm still going to be left with 4 queens, so 4 out of 7 for that probability. Now on the other side, if my first card was a queen, right, I'm going to still have 4 kings left, which means its probability is going to be 4 out of 7 cards. And then if the first card was a queen, the chances of a second queen is going to be 3 out of 7. Alright, and then let's focus on the question that's been asked to us. What is the probability of us getting 2 kings? That's simply going to be a half times 3 on 7, which is going to be 3 out of 14, and that's going to be the answer for part B of this question. 3 out of 14, and that's the answer. Alright, moving on to a third example. Right, this time we're dealing with a couple of tennis players. Each week John and Paul play 2 sets of tennis against each other. Right, so they're playing 2 sets again, which is an example of a two-step experiment. They each have an equal chance of winning the first set, right, which means the chances of them winning is 0.5 or 1/2. Now, let's just put that as part of our tree diagram to start with, right? So they're playing two sets, the first set and then the second set. We're going to draw the tree diagram first, and then we're going to go ahead and fill the probabilities. Right, for the first set, they both have an equal chance of winning. So the chances of John winning, chances of Paul winning are both going to be 0.5. Right, now for the second set, again, John can win, or Paul can win, or in this case, again, John and Paul. Right, now we still have to fill out the probabilities in the second part of this tree diagram. Alright, so let's go ahead and read the second part of this tree diagram. When John wins the first set, his probability of winning the second set raises to 0.6. Right, now in the first set, this is where John's won the first set. Right, so if John wins the first one, his chances of winning the second one raises to 0.6, which means his chances of winning the second one raises to 0.6, which means what is his chances of losing the second set? If winning is 0.6, losing is going to be what is left out of 1, which is going to be 0.4. Now, finally, let's have a look at the third part of this question. But if he loses the first set, right, so which means if John loses the first set, he has only 0.3% chance of winning the second set. Now, this is the part of the tree diagram where John loses the first set, right? So when John loses the first set, his chances of winning the second one is 0.3, right? So which means the chances of him losing the second one is going to be 0.7. Right, so that's why I said it's really critical that we actually read these questions carefully as we're dealing with the probabilities of this particular question. Right, so obviously this question just wants us to show the outcomes in the form of a tree diagram. Right, you can list the outcomes as well and their probabilities. Right, so you can just go J and J. I'm just going to do the first one, so half times 0.6. The chances of him winning both the sets is 0.3, and then you can fill out the rest. Make sure when you do finish it off, make sure that all adds up to 1. Alrighty folks, one last question for today. Right, in tennis, if a player serves the first serve, right, we're again dealing with the tennis question, right, if the first serve goes out, the player takes a second serve. If it goes in, they don't need to take a second serve, so which means, right, so when the first serve goes out, they take a second serve. If the first serve goes in, there's no need for a second serve. Alright, so here are some information given to us. A player serves with the following probabilities. First serve going in is 0.55. Second serves going in is 0.81. Alright, so there's two serves here, fellas, right? So first serve going in, right? I always like to write the complementary because we're going to be needing that as part of the tree diagram, right? If the chances of the first serve going in is 0.55, what do you think is going to be the chances of the first serve going out? Right, that's going to be what's left out of 1. So 1 minus 0.55 is going to be 0.45. Similarly, if I focus on the second serve, the chances of it going in is 0.81. So the chances that the second serve goes out is going to be 1 minus 0.81, which is going to be 0.19, right? So we want to represent this information in the tree diagram. Alright, so let's go ahead and do that. So first serve, and then the second serve as the second part of the two-step experiment, right? When we do the first serve, we've got two options, right? Either the serve could go in, right, or out, right? What are the chances of the first serve going in? That is 0.45, and the chances, my bad, I did make a mistake there, guys. Right, the chances of the first serve going in is 0.55, and the chances of the first serve going out is 0.45. Right, now let's read the question again. If the first serve goes in, they don't need to take a second serve, right? Which means this part of the tree diagram is just going to stop there. We're not going to have a second serve because when the first serve goes in, we don't need a second serve. Right, let's go to the second part of the tree diagram. If the first serve goes out, we need a second serve. Right, so when we need a second serve, we've got two options. the second serve could go in, or the second serve could go out, right? Now let's go ahead and look at the probabilities. What are the chances of the second serve going in? That is 0.81, and the 0.19 is the chances of the second serve going out. Now there's a follow-on question here. They want us to do a tree diagram and hence find the probability that both the players' serve goes out. So which means the first serve out and the second serve out, right? So which means we're trying to find what's the probability of both the serves going out, right? That's going to be 0.45 times 0.19, which is going to be equal to 0.0855. Right? Now if the question doesn't say anything, right, if it is a terminating decimal, like is the case here, just write the full answer. But in a lot of circumstances, they would give you the number of decimal places they want the answer in, right? And that comes to the conclusion of our lesson in terms of two-step experiments, right? Thank you for watching, guys, and have a lovely day.